Now it's recording, I think, right? Okay. So this is the week 15 stuff. This is waves, sound intensity level, all that stuff. So number one, just kind of like introducing you guys to waves and what waves are. So a wave is kind of any disturbance in a medium, right? Here, for example, they have a wave going through a slinky, right, or a spring. So there's a disturbance in that medium. Medium is like the object, right, that you see a disturbance in. So sound waves, right, will be a disturbance of the medium of air, for example. This is kind of an overview of what we did for week 14 stuff, period, frequency, amplitude, all those different types of equations, but we won't get into these for this chapter. So there's two kind of examples of waves here. So we have traveling waves, and those are disturbances with a well-defined wave speed, and you have standing waves, and those are disturbances that oscillate in a confined region. So what that means is, for a standing wave, like, you generally kind of have it where it's they're kind of just oscillating like this back and forth, right? And a traveling wave is kind of a wave that kind of goes like this, right? And it just keeps going. So essentially, I guess the difference would be that for a traveling wave, you don't have like a fixed end, and a standing wave, you do have a fixed end. So for a standing wave, like, you might have like a pivot here, right, and a pivot there. And then as it kind of goes like this, all that you see is an oscillation between these 2 points, right? So that kind of is why I have the string here, right, or the line, right? So if I am looking at a traveling wave, no, I messed it up totally. So I have a traveling wave, right? Here's that pivot that I'm looking at. This is one point that I'm holding. A traveling wave would just be like this. So it just travels along the end, and there's no fixed end right here. But if I were to just have someone else hold the end here, right, then this would be a standing wave where there's oscillations between those 2 pivot points. So you see kind of it shot back towards me as well, to the point that it kind of let go of his end, right? So a traveling wave, we have one fixed end, one loose end. Standing wave, we have 2 fixed ends, and just kind of oscillates between those 2 pivot points. And then, yeah, I mean, we're only going to focus on traveling waves. Standing waves, it's not necessary unless you're studying for the MCAT. And we're not going to go over standing waves at all. But that brings us to mechanical waves. So mechanical waves would be motion of substances, right? Or the waves that involve the motion of a substance, right? And that substance is the medium. So if you have a sound wave, the wave going through the air is the medium, right? So medium is just the substance through which the wave travels. And then obviously, disturbance is a wave, passes through a medium, and it displaces the atoms, right? Displaces the objects, particles and stuff in the medium that it's going through. Let's see here. So with that disturbance, with that wave that you have, they travel at a specific wave speed, and that wave transfers energy, but the medium itself does not travel. So that's kind of a weird way to think about it, right? It's maybe counterintuitive in the sense that if you have, for example, this ripple of water, you see the waves of water moving, right? And if you're on a beach, you see kind of the waves coming towards you. Well, that's not necessarily the medium itself, the water traveling. It's more so the waves that are transferring energy. So the medium itself stays the same. It's just that the waves will transfer energy. So the medium as a whole does not travel. It's just that these specific points, right, throughout the medium will kind of move themselves, and I'll kind of explain this in a sec. But you have the wave having a speed that imparts a specific energy, right? And the wave propagates that energy, but the specific medium itself doesn't move, right? So if I were to just kind of like look at the center of the water here, if I throw a rock in the middle, I see those waves move like this. The waves are propagating. There's a wave speed. There's a transfer of energy. But if I were to, like, for example, measure the volume of water in the center here, the volume of water didn't change, right? So the medium itself, the core, property of the water itself, the amount of volume it has, those properties didn't change. It's just that there's a transfer of energy. That transfer of energy that you see appears like the waves that are moving water away and away from the center. So it's just an appearance that there is a movement of the medium, but there's no actual movement of the medium. It's just that the wave speed is transferring energy, and we see that transferring through a wave that we see. So it just appears like the medium is moving. So it does not transfer any material or substance outward from the source. These are electromagnetic waves, matter waves. You're going to get into this in 132. Yeah, we're not going to go over these at all. So for the classes of waves, we have transverse and longitudinal waves. And the easiest way to kind of think about these is just kind of how they move, right, throughout the medium itself. So for a transverse wave, the direction of the disturbance is perpendicular to the direction of motion. So direction of motion of what? It's the direction of motion of the wave itself. So you can see here, if I did that spring like this, right, the spring moves from left to right, right? Okay, let me do that again. So kind of goes that way, right? Whatever. So the wave itself moves from left to right, but if you look at any specific part in the string itself, right, then you see all it does is actually move up and down. So the medium itself, right, will just move up and down, kind of like, or at least like these specific points will move up and down, right? But then the actual wave that you see, the peaks, those will move left to right. So the direction of the wave, the direction of that disturbance, left or right, but then each specific point of the medium, like the physical points of the string, will just be going up and down. And I have like a little animation that I can try and show you guys here. 1 second. So let me pull it up here. So it's what's it called? PHAT, Interactive Simulations, Wave on a String. So if I try, here's like a loose end, right? Or no end, my bad. And I want to have it kind of oscillate like this. So if I speed up the frequencies just a little bit and I go in slow motion, if you look at every single green circle, the green circles are just moving up and down, right? The green circles are just moving up and down. But you can see the peaks, the individual peaks right there, they're kind of moving left to right. So if I look at this peak right here, like look at the formation of this peak. Okay, that peak starts moving to the left, or moving to the right, my bad. So the actual wave itself is propagating from left to right, but every single individual like particle or piece of the medium itself, right, if we just kind of blow it up, all we see is that the particle is moving up and down. The medium itself is moving up and down, but the wave is moving left and right, right? So that's what we see there for the wave. Now, if you have a longitudinal wave, right, it's a little bit different because it's not the medium like particles moving up and down anymore. It's that the direction of the disturbance is along the direction of motion. So if I have a spring, right, if I stretch that spring from the last chapter, it's going to just move the spring itself, right, will just move left and right, and you see the waves moving left and right as well, right? And an example of a longitudinal wave would be sound waves, right? So if you kind of think about your average, like, I don't know if you've just seen just any cartoon or something like that where the waves kind of go like this and that for your sound waves. So that's kind of what's going on here, where the longitudinal waves are just, you have the motion of the wave itself being left and right, as well as the disturbance of the particles themselves being left and right as well. So essentially, it doesn't just have to be left and right, it could be up and down as well. It's just that the disturbance of the medium itself, so if you're disturbing air or if you're disturbing water, for example, then that disturbance of the medium is also the same direction as the disturbance of the wave itself, right? So if we looked at the previous example, you saw the waves propagating left to right, but the individual particles moving up and down, right? But for a longitudinal wave, for sound waves, if you push the medium or you act upon the medium, right, left and right, up and down, whatever, then the actual particles themselves will move in the same direction as the waves, right? So that's what you see with longitudinal waves. Specific example here with seismic waves, we don't really have to know these, I don't think, so I'll just skip these over. But that's what I was talking about with sound waves, right? So if you have these sound waves, what they do is compress the air in front of it. So if you have like a speaker blasting music, it'll compress the air in front of it, and that compression, that specific compression, that transfer of energy, right, is the disturbance that we see that travels through the air, right? And so that's why I was saying like a sound wave is a longitudinal wave, because whatever kind of disturbance it's causing through the medium, the wave is moving in that same direction as well, right? So we see these molecules, the air molecules, they're being compressed. Here's the motion of the wave. Here's the compression as well, right? So it's the disturbance of the medium in the same direction of the wave propagation as well, right? And I guess maybe a little bit detail here is just the motion of the sound wave itself is determined by the properties of the air. That's not something you really have to know, but just kind of, I guess, more power to you if you know it. Wave pulses will just be like individual waves, quote unquote, that we see. So if you flick that string from before, right, this would consider to be a wave pulse, right? So think about pulse, like, I guess the easiest way that I kind of relate it is that if you were just looking at like your heart rate, right? You know how it goes like, so that's like a wave pulse kind of, right? I guess that's a nice way to relate it. So don't flatline, right? We don't want to flatline, but that's kind of what I think about when I see a wave pulse. So just kind of like one individual part of a wave. Yeah, go ahead. Did you have a question?
So those like one peak?
Yeah, well, yeah, kind of, sort of, yeah, one peak, but it's basically like just, I guess just one section of a wave. I'm not sure if it's like one peak necessarily. Yeah, go ahead.
Is it either those feathers, like the ones you see at the gyms, or you like swap?
Yep, exactly, yep.
Smooth.
Yep. And then this is a kind of an example of what goes on with like each wave pulse. So it says the curvature of the string due to the wave leads to a net force that pulls a small segment of the string up or down, right? So if I flick that string like that, right, where I have this peak here, as that wave propagates, what do you see? The peak kind of moves throughout, right? So if I go back to that little animation there, you see the peak moving throughout, right? So essentially kind of what it does, like as that peak moves, right, you see that here's the peak, it brings up the other particle next to it upwards. I don't know, that's kind of hard to see. Let me see if I can slow it down a little bit more. Oh, that's not it, my bad. So essentially, like, if I'm forming the peak over here, right, what I see is that this particle, as that peak moves, is being pulled up with it, right? So as that wave propagates, as those peaks like move to the right, what you see is that the particles that were like at the bottom get pulled upwards so that they can form a continuous peak, basically. So like you see the peak moving from left to right like this, seems pretty continuous. The way it's continuous is that you have those little particles there that are being pulled up to form a peak at every single point, basically. So I don't know if can you guys like see that? Does that make sense, sort of, right? I just want to time it perfectly. So like, now I'm forming a peak. So then it brings it up, comes down, and sort of. I don't know, my arm just gets in the way. But does that make sense? So as that wave propagates, it pulls any of the other parts of the string with it, so it can form that little wave. So let me try and like do it with the string here. So as you kind of like form the peak, right? Essentially, shit. Okay, this is not gonna work. All right, you want to hold this real quick? So as I kind of like try and form a peak there, you see that it brings up these like parts of the string with it. So you see, this was at the bottom first. When I flick it up, all those other ones come up top as well, right? So whenever I have that disturbance there for the wave, what I see is that any parts of the medium that were at a lower level will essentially be pulled up to form that continuous peak or that continuous wave, right? So it says here that as the wave reaches this point right here, the curvature of the string leads to a net force that pulls the string upward to reform that peak, right? Because otherwise the peak would just stay flat, right? So flick it up, that peak needs to form here now. So in order to get that formation here, this has to move upwards to where this part of the string here will now be flat, and now here this will be formed upwards. So that way you can get that peak here, right? This will go flat, and now you have a peak there. So this was brought upwards. Make sense? And then for here, right, that's the other like point that I was talking about. So where you have that first peak and now you have that second peak, what happens here is that this falls flat. So as the wave kind of propagates this way, the other particles that were of the medium that are left behind will go flat, right? So like when I do the string and I flick it, the wave propagates, and then all the other particles that were behind it will just kind of go flat a little bit, right? So whenever you're thinking about how the waves move, especially if you have a graph, you see that there's like a backside and the front side to the wave, if that makes sense. So if I think about this is my backside and this is my front side of the wave, right? My backside is always going to be brought down because then it wants to be flat. And then my front side is going to be brought up this way to form a new peak, right? So the backside of the wave curves downward. The front side will be brought upward in order to form new peaks as you go along, right? In order to form a peak, to have some height, you have to have them move upwards. So if I'm moving to the right, then I have to have all of these be pointing upwards in order to form a new peak. That way, whatever you see kind of here will be flipped because it'll be pulled upwards. And then whatever you see here will be brought downwards to where if I were to kind of shift it over, right, and look at the new peak, I would kind of see something like this, where this is all flat now, right? So back side of the waves brought downwards, front side of the waves, it's pulled upwards, right? And if I were to draw it throughout the whole thing, if this is one whole wave cycle, right? This is all downwards here, 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 up until you get to the peak, and then it gets pulled upwards every single point here. That's your front side of the wave. Here's the new back side, right? That's all pulled downwards. And then here's another wave there, right? So if I were to continue this, I see downwards, downwards, and then upwards again. So the idea here is that there's a back side and a front side to the wave. Back and front. The front side is pulled upwards to propagate that wave forward, and the back side is pulled downwards to kind of have it where it's just continuing the wave along, and anything over here is just done, flat. Make sense? All right. So yeah, and this is just kind of a reiteration of the animation that I showed you guys earlier. So all points on a string would simply just move up and down. All they're doing is moving up and down. Only the wave is what appears to be traveling to the right. So the wave appears to be traveling to the right, but the individual string pieces will just be moving up and downwards. And so this is what I was talking about, like the front and back like pieces of a wave. So they said a wave on a string is traveling to the right. At this instant, right here, the motion of the piece of the string marked with a dot would be what? So if I'm splitting it up to here's my back side of the wave, here's my front side of the wave, right? The back side would have everything go downwards like this, so it's pulled downwards. The front side, remember front, that's what's going to be causing the new peak. So the front side is going to want to be pulled upwards, right? In order to form that new peak and have it kind of flow along, right? So the front side of a wave moves upwards, back side moves downwards. And so the only thing is that the wave is moving left to right, but the individual particles themselves, the medium itself is just moving up and down. So that would eliminate right and left. And so you just be looking at up and down, whether or not it's backside or front side, right? And so basically here, what did I want to say? Shoot. I don't remember, but that's just the gist of what's going on here. Front side, back side, and that's how you kind of draw them. And that's constant for all of the waves. But when we're talking about wave speed, when we're measuring wave speed and stuff, we assume that the wave speed does not depend on size and shape of the pulse, how the pulse was generated, and how far that pulse has traveled. So that's if you have no dispersion of the medium, right? And then wave speed is determined just by the properties of the medium when dispersion is absent. If you have dispersion, wave speed is dependent also on the wave shape. So I'll get to kind of what we mean by all this stuff here in a second, but basically for your wave speed, if you don't have dispersion, it's only dependent on properties of the medium. And if you do have dispersion, it's the properties of the medium, and it can also depend on the wave shape itself. Now, when we're talking about properties of the medium, right, properties of the air, properties of the string, we're looking at, specifically at least for a string, linear density. So linear density, mu here, is the ratio of mass to length of the string itself. So if we wanted to calculate the wave speed of a string, then that's equal to your force of tension that you pulled the string with. So if I want to measure the speed, right, the speed of a wave, well, I whipped it with a certain force, right? So that's a force of tension there. And so that force of tension divided by the linear density, the properties of the spring or the string itself. And then if I take the square root of that, that gives me the velocity of the string. That's just an equation that you kind of have to know, but it's on the equation sheet. But just there's I don't know if there's a derivation for it, but for linear density, it's just that's the properties of the string itself. It's the mass to length ratio of the string. And then for the velocity of the string, it's the square root of the force of tension that you apply to the string divided by the string properties. So this is wave speed dependent on properties of the medium. So if we were to ask for a wave pulse on a string to travel twice as fast, the string tension must be what? So if I wanted 2 times the speed, right? Well, if this is my speed, square root of force of tension divided by linear density, if I want 2 times that, then if you have a 2 outside of the square root, then if I would it would be 4, right? So 4 times force of tension divided by your linear density, take the square root of that, square root of 4 would be 2. And so you're left with 2 on the outside, right? Make sense? So, yeah. So you would be increased by a factor of 4 for the tension in order to have twice the speed. Now, there's another quick check. It says there are 2 wave pulses that travel along the same stretch string, not spring, string, one after the other, which is true. So they're the exact same string, right? And there's 2 of these pulses. Then they're asking you which one has a faster wave speed. So really, I think, I'm going to just kind of fast forward here just to make sure. I don't think we ever get into the dispersion wave speeds, because then dispersion, it would also be dependent on wave shape, and I don't think that we ever have an example of that. So we're only focused on wave speed when there is no dispersion. I don't think they have a condition with the dispersion in it, so I'd just be worried about without dispersion. And so given that wave speed without dispersion is only dependent on the properties of the medium, not the wave shape, then if we're looking at here, they said it's the same stretch string. So should we have the same string properties or not? If it's the exact same string, do we have the same string properties?
Yeah.
Exactly, right? So same string properties. And string properties, remember the value for that was the linear density, which was the mass divided by the length of the spring. So the linear density is the same, right? And obviously they didn't give any indication that the force of tension was changed. Then we should see that the velocities would actually be the same. VA would equal VB because the shape of the pulse does not affect wave speed. So you might think, well, okay, if he had this might look like a more vigorous whip or something, so you might think it'd be going a lot faster, but this is just the shape of the wave, right? So, I mean, I could apply a small force, but I have it where it's really kind of long, so I might have a really high kind of amplitude or a really large wave pulse, or I could just I don't know, also have that same wave pulse, right? That same really long one, but apply it with a lot more force, and so it goes really fast. Same shape to it, but totally different speeds. So what you see here is that you could have the same shape, you could have a different shape. Shape doesn't depend, or doesn't matter when it comes to determining the wave speed, right? Whether it looks like this or it looks like that does not matter. The only thing that matters is the force of tension you apply and the properties of the string itself. They gave no indication that there was a different force of tension, so the only thing that we have here, any indication of, is the linear density, right? Because the linear density is the same, because it's the same string. So the linear density is the same, and we're assuming there's no change to the force of tension, then your velocity should be the same. Make sense? Okay. So this is an example. I'll just skip to this part here. So it says, actually, let me go back here and actually read the problem. Okay. So spiders are very sensitive to vibrations. An orb spider will sit at the center of its large circular web and monitor radial threads for vibrations created when an insect lands. Assume that these threads are made of silk with a linear density of 1.0 times 10 to the negative 5 kilograms per meter. So that's our linear density right there, right? Under an unknown tension. It It says if an insect lands in the web 30 centimeters from the spider, then 1.5 milliseconds later, the spider feels that resulting vibration. Now they're asking you for the tension. So you know that the linear density is 1.0 times 10 to the negative 5, right? And then you have a specific distance, 30 centimeters, that the spider feels after 1.5 milliseconds. Well, now you're just trying to figure out the tension, right? Well, what is this an indication of when you have distance and you have time? What could you figure out? Velocity, right? Velocity. So if you have that distance, the 30 centimeters, and you have that spider feeling that vibration of that 30 centimeters, right, after 1.5 milliseconds, then you can figure out the wave speed. Because if there's that 30 centimeter like distance between them, right, let's say like, yeah, so if there's 30 centimeters between them and the spider only feels the vibration 1.5 milliseconds after like the insect comes into contact with the web, then that wave speed would just simply be the distance, right, or the displacement between the insect and the spider divided by the time it takes for that wave to reach there, right? So that's our speed. If we have our speed, we want to figure out our force of tension, and we have our linear density, then we can just rearrange the equation and figure out what force of tension is, right? So the speed there of the wave would simply be the distance between them, right? Essentially would be kind of like the distance of the wave, right? And that's 0.30 meters, right, or 30 centimeters between the spider and the insect, and then divided by how long it takes for that wave to arrive to the spider. And that was 1.5 milliseconds. So 1.5 milliseconds is the same thing as 0.0015 seconds. So we should say 0.30 divided by 0.0015. We should get 200 meters per second as the speed of the wave. So that's the speed of the wave. 200 is equal to the square root of force of tension divided by linear density, right? So if we just take this, if we square both sides, we get rid of the square root over here. And so we're just left with v squared times your linear density is equal then to your force. And that would just be equal to 0.4 newtons. So you take it at 200 meters per second, that speed or that velocity, square that, multiply by your linear density, which was like 1.0 times 10 to the negative 5. And if you do that, you should get your force, the force of tension, right? So that's not too bad. There's also an equation for the speed of sound here, right? Or the velocity of sound there. And that's given by an equation for gases, and that's dependent on a couple of different factors. So it's dependent on the temperature in Kelvin, temperature of the medium, and that's temperature of air, right? And then it's also dependent on the mass per particle or per molecule. Dependent also on Boltzmann's constant and a factor called the adiabatic index, right? And that's just a constant that depends on the specific gas, right? So if you remember, like, what's it called? Like Young's modulus and Bulk's modulus, right? Or the bulk modulus. Those will be different, like, constants that will be dependent on the specific object or medium. So in this case, this is just another one of those types of constants. The adiabatic index is just simply a constant that depends on the specific gas. So, and that specific index or constant is equal to 1 plus 2 divided by the number of degrees of freedom per molecule. So if we're looking at an ideal gas, right? Remember for what I said about the degrees of freedom in the last session that we had here. So I said for every single ideal gas particle, you have 3 degrees of freedom, 3 ways of storing energy, Vx, Vy, and Vz. So for an ideal gas, right, the adiabatic index would be 1 plus 2 divided by the number of degrees of freedom per ideal gas molecule or particle. And so that would just be 1 plus 2 divided by 3, right? Or 1 plus 2/3, basically. That would be your adiabatic index. Your Boltzmann's constant is 1.38 times 10 to the negative 23 joules per Kelvin. Temperatures in Kelvin, and this is mass per particle. Don't plug in molar mass. It's mass per particle / mass per molecule. And generally, like, this is just kind of a derivation of all this stuff, but we have already kind of figured out what the speed of sound in air is at 20 degrees Celsius at least, and that's 340 meters per second. I don't think you're ever going to have to, like, use this equation necessarily. I'm not sure if it's on the equation sheet or not, but generally speed of sound is 340 meters per second whenever you're solving a problem that involves speed of sound. Speed of light is 3 times 10 to the 8 meters per second. That's another constant. It's probably going to be on your equation sheet. There's not really much that you have to know on this slide other than that. This is a very quick example problem as well. It says if you see a flash from a lightning strike, and then 8 seconds later you hear the crack of the thunder, how far away did the lightning strike? Well, we know speed is just equal to distance divided by time, right? Well, if the speed of sound is 340 meters per second, and I only heard sound of thunder 8 seconds later, if I just take 340 times the time it took me to hear it, 340 times 8, that'll give me the distance away that, lightning strike was. So 340 times 8, that gives me how far away it is. But yeah, this is where I start falling apart in terms of my knowledge in physics, because I've tried so many times to fully understand this stuff, and always I feel like it's just a little iffy for me. So snapshot versus history graphs. So the idea with developing snapshot and history graphs is the fact that we don't I guess we can't capture the entire motion of a wave just by looking at one graph. We have to have two different types of graphs to display different information relative to the wave motion. So when we're looking at snapshot graphs show us the entire wave at a single point in time, right? It shows us the behavior of the wave at a specific instant in time, right? So as time increases on a snapshot graph, what you see is the propagation of the entire wave itself. It shows you the behavior of the wave itself, the propagation as you increase in time. History graphs, on the other hand, show us the motion of a single location on the wave for all times. So remember with that animation that I was showing you guys earlier, a history graph would show us the motion of one of those green beads, right, for all time, right? So it just shows us how the motion of that green bead would change at any time throughout the wave, right? So essentially, what that graph might look like is just a series of moving up and moving down, moving up and moving down. So all the history graph shows you, history as in time, it shows us throughout all of time, throughout all of history, what happens to that green bead, what happens to that specific location on that medium or throughout that wave, right? So as the wave propagates, you see those green beads just moving up and down. If I were to focus on one of those green beads, and I want to draw a history graph, think of, it looks at the history, all of time, throughout all of history, what happens to that green bead? Oh, it just moves up and down, right? So that's what a history graph kind of shows you informally, right? But a snapshot graph, you just take a snapshot, take a picture of the wave as it moves throughout time. So if I were to just have this wave right here, if I want to take a picture at this moment, that's a snapshot. Another moment, snapshot. Another moment, snapshot. You see at every single point, the peaks will kind of look a little bit different because the wave has propagated already. So if I looked at, let's see here. If I looked at this specific point, I took a picture of it, that's a snapshot, right? If I let it play again, that's a snapshot. So let's say that was 2 seconds that passed during that time period, right? Now it looks like this. So snapshot graphs will basically take pictures, right, as time progresses of the motion or the propagation of the wave in its entirety, right? History graph will just show you what happens to a particle throughout the history of time. So hopefully that kind of makes a little bit more sense with regards to snapshot and history graphs. The concept themselves aren't hard to understand in my opinion. It's just that converting between snapshot and history graphs is where things fall apart. So snapshot graphs is our entire waves at a single time point, right? So if I were to look at this snapshot graph, this is at time 1, time 2, and time 3. So I can see here, if this is my entire wave, if I'm just looking at x equals 1, right? This is position 1. Let's not necessarily say a bead, right? Let's just say this is position 1 that we're looking at. So at wave time 1, this is what the position looks like. At wave time 2, this is the same position, but all of a sudden now it's elevated. At time 3, well, now it came back down. At time 4, well, now it's flat. So that just shows you the progression of the wave, right? So that'll be that example of the bead. At time 1, it was brought upwards a little bit. The wave propagates throughout it, right? Now, it's sort of at its peak, and now it's coming back down. Time 3, now it's flatlining a little bit. Time 4, now it's fully flat. So it shows you basically how the wave kind of comes through a specific bead, right? So the bead is stationary, that's the medium, that's the string. It shows you, okay, well, if I had that little string there again, the very end of the string, I'm waiting for something to happen there. As the wave moves through, then I see a specific like alteration of that specific point. So as the wave propagates, as time 1, time 2, times 3, times 4 goes on, then that bead might go upwards and downwards and flatline and come flat, right? So just for a snapshot graph, take a picture at every single time point, shows me what happens to a specific point as the wave moves through it, right? History graph will show me, okay, well, if I looked at that specific point, what happens to the position of that specific point? So as time 1, time 2, times 3, times 4 goes on, I see that particle moving upwards, reaching a peak, and then moving downwards, right? So a history graph would just show me along the entirety of a specific time interval, along the history of time, what happens to that particle. Oh, it just moves up and down, right? It just moves up and down. That's all, right? So history graph will show you motion of one specific location on a wave for all the time periods. A snapshot graph will show you an entire wave, how it propagates and how it disturbs a specific point at specific time intervals. So if I took a picture at time equals 1, this is what the green bead would look like. If I took a picture at time 2, this is what the green bead would look like. Time 3, this is what it would look like. Time 4, this is what it would look like, right? So for history or for snapshot graphs, what you see is that the axes are different. For snapshot graphs, you see a your axes, your y-axis would just be like, well, I want to say, yeah, forget the y-axis. If I'm just looking at the x-axis, yeah, I'm just looking at like, this would just be the shape of the wave propagation. So x-axis would be like your specific distance along the wave, right? Your specific bead point. So if I'm looking at x equals 1, this might be the green bead, right? And then for every single snapshot graph, they're different points in time. But what you see along the x-axis is just the position of the medium or the position of the particle that you're looking at. And then the y-axis would just show you like basically how the wave looks like, right? The behavior of the wave. History graphs, on the other hand, will show you time on the x-axis, so as time progresses, and then on the y-axis, the actual y position of the particle or the green bead itself. So as time goes on, as the wave propagates, I see the bead move up and then move down. So history graph tells me on the x-axis time, and on the y-axis it shows me the displacement of the green bead, right, or the medium. But I think that's probably it for a snapshot graph. Is just displacement as a function of position at a single instant of time. And then, yeah, you can plot a sequence of snapshot graphs, each one at a specific time interval. And x-axis would just show you your position of the medium right there, and the y-axis would just tell you like how that medium like has changed position. So if it's kind of weird, but like x-axis would just tell you like which bead you're looking at, essentially, like red bead, green bead, whatever. And so you just pick a position, and then your y-axis would just tell you like if it's at a positive displacement, or if it's moving downwards, or if it's moving upwards, whatever, like where it's located essentially, as the wave propagates at specific time intervals. So if this was time t1 right here, where the let's say this was the green bead, it's at the top here. If I look at time 2, for example, or actually, no, I take it back. Let's see here. Okay. I don't know, this is a weird graph, but yeah, honestly, if I just go back to these ones up here, if I choose this position, this is the bead I want to look at. At time 1, it's right here. At time 2, it's right here. So it just shows you how the position of the bead will kind of change at different instances in time. But yeah, and these will show you the motion of the wave, but not the motion of the medium itself. So it'll just show you the wave propagation. So it shows you the wave as it moves from left to right at different time intervals, and then the position of like the specific like bead or like the specific part in the medium at those different times. But it doesn't show you the motion of the medium itself. It just shows you snapshots of the motion. History graphs, once again, will just show you how that medium will move over time. right? So it'll go up and down. The green bead will move up and down as it goes. But yeah, this is an example of how to kind of look at these snapshot graphs. So if you have a snapshot graph at time equals 1 second, where you have a wave pulse moving at a speed of 1 meters per second, if they were asking us which graph shows the wave pulse at t equals -1 seconds, right? Well, all I have to do is just look at, okay, well, here's my wave speed, or my wave speed here, 1 meter per second, right? So at t equals -1 seconds, right? Then think about how many seconds away that is. -1 second, it's just weird. -1 seconds is weird. But if I were just to say, I'm looking at 1 second, and I go backwards to -1 seconds. Well, what's like the time interval here? What's the difference in time, basically? Just 2 seconds, right? So this would be like, it's stupid how they put -1. I would much rather preferred them to say like, oh, let's do 1 second here and then like 3 seconds there, right? That would have been easier to think about. But if it's -1 seconds, it just means that there's a time interval that you move backwards 2 seconds, right? So if I know the wave speed is 1 meter per second, then after 2 seconds, how far should I travel? If the wave speed is 1 meter per second, and I traveled backwards 2 seconds, or I traveled 2 seconds in general, I travel 2 meters, right? So 1 meter per second times 2 seconds, that'll give me 2 meters, right? Well, that just means I'm going to be moving backwards 2 meters. So I want to figure out, like, 2 seconds ago, -1 seconds, what was my displacement, or how did my graph look like, right? So I have to essentially move this graph back 2 meters. So I just pivot it over, if I just pivot like here, 2 meters, right? Then I should see graph A would be what it would look like, right? Because I essentially just took this part here and moved it back 2 meters, right? 2 seconds ago, 2 meters. So if this little like half point here, right, of the two triangles, then if that was at 1, then I move it back 1 meter, 2 meter, so it's at -1, right? If my peak was at 0 here, I move it back 1, 2 meters, so now my peak is at -2. Make sense? This is where, like, these two examples right here are just where it gets difficult. But this says the graph below shows a snapshot graph of a wave on a string that is moving to the right. A point on the string is noted right here. Which of these choices is the correct history graph for the subsequent motion of this point? So if this is a snapshot graph, right, this is just a picture that you took at a specific time interval, right? A snapshot graph, like I said, will show you how the wave moves at different time points, right? So this is just the behavior of the wave. That's what the wave peak is going to look like. That's what the pulse looks like, right? It's just going to look like this at every single time interval. But it's just going to move to the right. So let's say this was time 1. Time 2 might look like this. Time 2 might look like that. Time 3 might look like this over here. So it's just the wave itself, the overall graph moving from left to right. That's your snapshot graph idea. The history graph, once again, will show you how individual particles throughout that medium will move, right? Do they move upwards? Do they move downwards? What happens, right? So if I were to basically like draw different time intervals, like this was time 1. This is time 2. Let me draw that in a different color. That's not good. All right, hold up. I want to draw this in a way that makes it easier to see it. So okay. So this is time 1, this is time 2, and let's say this is time 3. So if I'm looking at, the idea here is that I pick a position, I pick a bead. If I look at this position right here, in the original graph, this black graph right here, what's the position? If I'm just looking at the black graph, the original graph, right? And keep in mind, like when I say X, like it just means like, or at least not about X. Let's say like if I'm looking at the Y-axis instead. Y-axis would show me like the position of the particle, right? Up or down. So right here for the black graph, if I'm looking at this point, am I upwards, downwards, or am I just zero? I'm flat, right? Right here I'm flat. If I look at time interval 1, this pinkish graph here, there's that intersection point right there. Have I moved upwards or downwards? Moved upwards, right? From like, once you move to the different time intervals, forget the black graph. Just look at, here's that point. Where's the position of that point at that specific time interval? So along the pink graph, this position, that green bead, has moved upwards to here. At time 2, same green bead, same position right here, or same bead that we're looking at, same particle. At time 2, where's it at? What? Right here, right? Around the peak, right? So at time 2, it's increased all the way to the peak. At time 3, this green graph right here, where's the green bead now? It's downwards now, so it's down here, right? So it went from the peak to downwards again on the green graph. So what you see here is that, once again, kind of that idea of that animation that I was showing you, that it moved upwards and then moved downwards again. Now, when you're converting between snapshot and history graphs, because there's differences in slope, right? This is like less steep and this is more steep. Picking your graph, you have to pick it on, I guess you have to pick it based on like, essentially kind of like the slope of the wave propagation, if that makes sense. So as time intervals increase, right, do you see this slope coming into contact with the bead here first, or do you see this one coming into contact first? It's kind of a weird question. Like, I guess, does the backside of the wave come into contact first, or does the front side of the wave come into contact first with the bead? What? Front side comes first, right? Because obviously you're moving front of the wave, so front of the wave hits it first. So the front side of the wave hits the particle first. So that particle, that green bead there, should increase or move upwards in the same way as the front side moves. So it should move in that steeper way, right? So it should move very steeply, time 1, time 2, because you can see here, those two, if I look at, there's my position and there's my position. So the increase or the movement upwards, at least for those first 2 time intervals, is based on that front side of the wave. Once I get to time 3, is the front side or the back side causing the motion of the wave at this point? The back side, right? Because if I look at the back side here, here's the back side. Oh, well, it dropped down here. So the back side kind of caused the green bead to come downwards a little bit. So essentially, if I'm looking at my graphs here, right, what I see when I draw these multiple snapshot graphs, I see a movement of the particle upwards and then a movement of the particle downwards, right? So that automatically eliminates C and D, because I don't see it moving downwards first and then upwards. I see it moving upwards and then downwards, right? So if I just repeat these drawings over again and I look at, okay, well, how far is the particle now? Is it moving upwards or downwards? Then I can see if I just drew this a bunch of times, right, then it has moved upwards, at least initially, right? So that eliminates C and D. Now I'm looking at B and A. We can see here that B and A, well, A is almost like identical to the actual graph. B is a little bit different, right? Well, I don't want to just eliminate A just because it looks like the original graph, right? I just want to kind of think about this a little bit more logically. So, like I said, the front side comes into contact first. So it should kind of like, quote unquote, increase or move upwards at a rate of the front side. Does that kind of make sense, sort of? So like, in that case, if the front side is coming into contact with the bead first, then it should move upwards in that same kind of slope fashion or that steep fashion as that front side of the wave. So it should increase at a rate of the front side first. B is the only one that has that steepness of the front side first. And then you see here, as you increase in the time intervals, by the time we get to T3, the movement of the particle, upwards or downwards, right, is dependent then on the slope of the backside. And so the slope of the backside looks like this, right? So the idea here is then like, okay, well, is the particle now, once we get to that backside, is the particle moving upwards or downwards once it reaches that backside? Because if you go, like, if you have, here's the particle that you're looking at. If this was that steep side, the front side, then all you see as you move to the right is movements upwards, right, for that front side. For that back side, when it's looking like this, you see it goes from here to there, right? So that back side causes a movement downwards. So first of all, you have to look at front side, back side. What types of movements do they cause, upwards or downwards? Then front side, steep, not steep. Back side, steep, not steep, right? So if I look at B, first of all, for that front side, I see an increase. I see a movement upwards. For that back side, right, I see a movement downwards. So first, like, I have to look at, as I increase in time, what happens? I move upwards and I move downwards as I increase in time. Okay, I move upwards and downwards. Well, this is upwards and downwards as well. So why isn't it A? Well, after I've determined that it's upwards and downwards, not downwards and upwards, after I've determined that it's upwards and downwards, then I have to look at, okay, at which rate does it move upward and downward? Well, it moves at a rate first of the front side and then the back side. So it moves upwards at a rate of the front side, it moves downwards at a rate of the back side. So that's why it's B. Does that sort of make sense? I'm just going to preface that here by saying, like, I don't think, worst case scenario, you see like one or two of these as a multiple choice, that's it. So.
I mean, it makes sense. And obviously, it's shocking how like complicated it can be.
Yeah, like I've.
And it's so interesting because like, oh, it's just like waves.
Yeah.
Like, waves, like when they're intersecting waves, and then the movement like where's
Yeah.
bringing down up.
It's gonna be square.
We're like, yeah. And then, like, what is this? What is this point? At this point, and then we're like.
Yeah, I honestly, I remember I don't know if I did have a question in the snapshot graph on our exam, but if I did, like, I'm just telling you, I went into the exam not knowing, like, snapshot, and I was just gonna give up. I was just gonna circle something. Like, it's just too much.
Your brother and I were talking about it because one of the quizzes they decided to throw flux out of nowhere. Like,
Oh, yeah.
completely threw us off because of it. So used to like.
I don't know. Like, I just hope they don't throw like some of these more like nuanced like topics in here, but I don't know. We'll see. But then, after spending so much time converting from snapshot to history, now we have to convert from history to snapshot. So, it says the graph below shows a history graph of the motion of one point on a string as a wave moves by to the right. So remember, a history graph will show you how the particle has moved, right? It moves upwards and then moves downwards and then upwards again, right? It says which of the choices is the correct snapshot graph now for the motion of the string. So once again, this graph tells us the point will move upwards, shoot downwards, and then gradually move upwards again, right? So if I'm looking at a snapshot graph, once again, the snapshot graph will give me like what the wave looks like at different time intervals, right? So I don't find it easy to convert from history to snapshot. I figure it's easier to go from snapshot to history. So what I do is I basically take every snapshot graph and I shift it to the right. And then I try to get from the snapshot graph to the history graph. And whatever one matches up to the history graph is the right answer. So if I look at shifting this graph to the right a bit, so it goes like this, like that, and like this, right? Well, as I move to the right, if I focused on, if this is my green bead, right? And this is my original graph, have I moved upwards or downwards? If this is my original and this is my shifting. So if this is like T1. So after T1, did it move upwards or downwards? If this is my original, right? This is my original and this is my T1. So it moved upwards. Yeah. So like if this is my original, right? This is my original. And then after t1 seconds, right, this is the wave that moved to the right. The wave has moved this way. So if this is my green bead right here, and this is my original, the green bead moved upward, right? Well, do I see a movement upward of the particle or not? Because remember, the history graph shows me throughout all of time, how does the particle move? The particle moved upwards, shot downwards, then gradually moved upwards again. So, this style of graph, right? This style of graph shows that as I shift the snapshot to the right, I see at least an increase in the position upwards, at least initially, right? So that tells me then that D and B, because they kind of have that same like style like this square root style is what I like to call it, right? Both of those, like if I were to shift this one as well, if this was my green bead, here's my green bead, did it move upwards or downwards? If the black is my original and I shifted it to the right, this is T1. Upwards again, right? So B and D at least match for like this section of the graph here, right? For this section of the graph here. If I look at A and C, if I shift this over like that, if this was my green bead, right? And this is my T1, what happened to my graph? Or what happened to my bead? It moved downwards, right? So that eliminates A and D because I have to see an initial movement upwards. And A and D, if I shift them over like this, I see that I move downwards, right? It has to reflect the movement, right? Now, B and D, I look at them and I'm like, all right, well, which one is the right one? So remember what I said about like, kind of like, what's it called? Front side and back side with like the rates of the movement and stuff. Well, if I'm, what do I want to say? I guess we'll, hold up. Would that work here or not? I'm not sure if it will. So I'm wondering, like, if you just take this snapshot here and you shift it to the right at T1, and we're just looking at a specific point here, and that moved upwards like this. Okay, never mind. So I see what I'm doing wrong a little bit here. So let's not look at the left region here. Let me look at the front of the wave. That's what I was doing wrong, I think. If I'm looking at the front of the wave here, right? Well, yeah, okay, no, that works. What I said before about like front side and back side works, is just I was just picking a wrong position. I worked from the left when I should have been working from the front side of the wave. So if I look at the front side of the wave right here, as that wave propagates, as it shifts to the right, this is T1. If this is my green bead right here, is it increasing? Is it moving upwards, I mean? Yes, right? Now, what is it moving upwards at a rate of? It's moving upwards at a rate of the front side of the wave, right? This right here is the front side of the wave, right? If this was a snapshot, if this is the correct snapshot, this is the front side of the wave. Remember, this is our history graph. The history graph shows us that this is the motion of the particle, the green bead, moving upwards and downwards. So it shows us that the particle, the green bead, moves upwards at a really fast pace firstly, and then shoots down immediately, and then moves gradually upwards again. So really it's the key of this part and this part. So both of these are moving upwards. They're just moving upwards at different rates. And if you compare these two graphs, B and D, you see this one is like gonna show us that movement, right? But here they have that initial rate as very steep, and here they have it kind of shallower, right? But like I said, that's where it gets kind of confusing, because you might think that, well, if this is the really fast rate, then this should be B, right? But like I said, and this was the mistake that I made earlier, you have to look at the front of the wave. So if this is my initial increase and it's very steep, then I look at the front of the wave. This is very steep, this is shallow. So if I've determined already by shifting the graphs to the right that there's a movement upwards, then D and B are my options. Because C and A, right, they've shown me that the green bead will move downwards. So A and C are no longer options, I'm looking at B and D. So I look at the front of the wave. If I look at the front of the wave, right, as that wave propagates, oh, that's horrible. As that wave kind of propagates, and I'm looking at this bead right here, am I increasing by the shallow slope, or am I increasing by the steeper slope? For like this part right here, because remember I said, like here you're increasing by the really steep slope. So that should make it B or D. Which one? D, right? Because here you're increasing, the front of the wave is that steeper slope. So remember, this is the front, like at least for your history graph. Your history graph is front here, and anything here is like the back, basically, right? So initially, what I see here, any increase or decrease or like moving upwards or moving downwards, should be based on the front of the graph for the snapshot.
So the snapshot is completely reversed from history. So
Essentially, yeah.
You have to look at it from the opposite.
Mm-hmm.
So
Yep.
like a mirror image of itself.
Exactly. So if you were to flip this over, if you were to flip this the other way around, then you see
What time will you end the session?
we're supposed to end it at 3, but
3?
yeah.
How long will you need? I just wanted to know that.
I don't know. Amit, what do you think? We're only slide like 30 out of 80, so I don't know.
You can take how much time you want. You can just like let me know.
Okay.
Four
Probably,
time?
yeah, probably no more than 4, I think.
No more than
yeah,
4?
no more than 4.
Okay.
Sorry about that. Thank you.
That's fine. Take it down.
Yeah, I'm recording it. Yeah. What? Yeah. Yeah. But yeah, if you think about it, your snapshot is basically, if you reverse it, you get your history graph. So if you were to take this, flip it from like right to left, basically, right, then you see it should kind of look like, well, hold up, this, like that, and then it should be shallower, and then like this. So that's what you see here. So your snapshot, I mean, this is the easiest way to do it, I guess, but I think if you aren't able to like flip it in your mind, just kind of breaking it down like that is also nifty. But yeah, snapshot, if you reverse it, you get your history. History, if you reverse it, you get your snapshot. So if I were to take this and flip it the other way around, then my snapshot should be, and that's what I see here. Make sense?
Hi. Do you need some more time?
Yeah. We someone else came over and they said we'd be here till like 4 maximum.
Oh, no problem.
Yep. Yeah. So this I think is just kind of like a review of last like week stuff. So sinusoidal waves you have for simple harmonic motion. The waves oscillate with a period t, frequency 1 over t. And then angular frequency equal to 2 pi times frequency, or 2 pi over t, which is your period, right? Now, wavelength, when we're looking at a graph here, it'll just be like the distance between your crests. From here to here, that's a whole wavelength right there, right? And then you obviously have from like your equilibrium position, or from like your 0 point upwards is your amplitude, from your 0 point downwards, that's your amplitude as well, just in the negative direction. Yeah, crests will have a displacement of the amplitude, positive amplitude, and troughs will have a displacement of negative amplitude, basically. So for a snapshot graph, the wavelength is the distance between the peaks of the wave. And it's also the distance traveled by a wave over one time period t. So if you have a snapshot graph, these are the snapshot graphs, right? From wavelength to wavelength, that's the distance between the peak. Or not wavelength, I said that the other way around. Crest to crest, that's your wavelength, right? And then that distance of your wavelength there should be the period. So that'll be like one wavelength per how many seconds, right? That would be your period. And then if this was a history graph, remember history shows you different time intervals, T1, T2, T3, T4. Then it shows us, once again, from crest to crest, that would be our period right there. So if this was like 10 seconds and this was 20 seconds, right? Because remember the x-axis for a history graph is your time. So from 10 to 20, your period then would be 10 seconds. So we'll get here into it in a second, but I want to see if I have like an example of it or not yet. I don't know. But yeah, basically for a history graph, you have like your displacement on the y-axis, x-axis is your time. From crest to crest on a history graph, that gives you your period. For a snapshot graph, that's your wavelength, and it also happens to be your period as well.
So if we were to try to find frequency, we want to use the history graph as opposed to the snapshot?
If you want to find frequency, for frequency, like you can actually, well, yeah, frequency, I think you would have to use a history graph, because for your history graph, you would have those time intervals right there. And so if you have from here to here, that's like 10 seconds, right? That's your period. Then 1 over your period, 1 over t, 1 over 10 seconds, that would give you your frequency. But for a snapshot graph, you don't have like your time values here, because you don't have T1, T2, because this is a snapshot. It's just a picture at a specific time interval. What you do have on the x-axis is different distances. So this is like 10 meters, this is 20 meters. Then from 10 to 20, you know your wavelength is 10 meters, right? That's all you can pick out from a snapshot graph. You can only pick out the wavelength. From a history graph, you can pick out the time, because time, history, you're looking at all of time. For your snapshot, you're just looking at specific time intervals and what's the distance like there for the wavelengths, right? So the wavelength is what you can pick out from a snapshot graph. History graph is you can pick up time, period, and frequency. I think that's it for at least like the sinusoidal waves. And then for velocity, or the speed of a wave, that's equal to your wavelength divided by your period, or your wavelength times your frequency, right? That's very simple, just plug and check equation right there. So if they were to tell us for this sinusoidal wave, what is the frequency, right? If I have a speed of 200 meters per second, this is my wavelength, this is my frequency. Well, first of all, is this a snapshot or a history graph? Snapshot, right? Because it's giving me distances on the x-axis, not time intervals. So think time as in history, x distances would be your snapshot. So with my snapshot, remember what information can I deduce from my snapshot graph? What information can I get from my snapshot? Just by looking at like distances from crest to crest or all of that? Well, technically, like right here is your period, yeah, but we don't have our time, right? Because here what we have is our x distances. So yes, from here to here would be your period, but on a snapshot graph, it would give us our wavelength. So you can see here, like this is 2 meters and this is 4 meters. So our wavelength should be what? 2 meters, right? So if our wavelength, our lambda here is 2 meters, this is times our frequency, or if our velocity is 200 meters per second, then our frequency should be what? 100 hertz, right? So that's B. Not too bad. This is, speed or velocity of a wave is equal to your wavelength times your frequency. Because remember, frequency is measured in like inverse seconds or 1 over seconds, which is hertz, and your wavelength would be in meters. So meters times 1 over seconds will give you meters per second. Yeah. But then this is the example I was talking about earlier. So if you have snapshot and your history graph side by side, right? Then you could pick out information from each one and come up with something. So if they're giving you the snapshot here, and this is the history graph there, they'll ask you what the speed of the wave is, right? So remember, speed is equal to your wavelength times your frequency, right? So if I have this snapshot here, if I go from 0.6 to 1.2, that's crest to crest, then I know that my wavelength is 0.6, right? Then if I look at my history graph, from 0.2 to 0.4, what is this? Your period, right? So that's 0.2 seconds is my period. period is 22 seconds. For frequency, I know frequency is 1 over your period, right? So 1 over 0.2. That would give me the frequency, right? So actually, did I do this wrong? I think I might have, yeah, I might have done this wrong. So forget that for a second. I don't think it's 3. So you have your wavelength. So this V is equal to wavelength times your frequency. If your wavelength is 0.6, and then your frequency, well, at least your period here is 0.2 seconds. It's your period. So your frequency is 1 over the period. And that's 1 over 0.2 seconds, or that's like 2/10, right? So then your frequency will just be equal to 5 hertz, right? So actually, no, it works out. Never mind.
Yeah,
I just did it. This is a weird way to do it, but yeah, 0.6 times 5 hertz then for your frequency should give you 3 meters per second. So forget what I said earlier. I just like came up with the right answer the wrong way. If that makes sense. I did 0.6 divided by 0.2, which is like, yeah, whatever. Actually, no, screw it. I did it right. Oh my God, I'm so tired. Your frequency obviously is 1 over period. So if you did wavelength times 1 over period, and your period is 0.2, then 0.6 divided. Yeah. So either way is right. I'm stupid. But yeah. So that's how you can pick out information from each graph and kind of figure things out like that. So now we're done with snapshot and history graphs, so we can get on to a little bit of sound. And sound, a lot of it is just plug and chug. There's not much that you really kind of have to understand. I don't even think they did they do Doppler stuff or no? What? Yeah. Maybe I'm just thinking about, okay, never mind. Yeah. So I don't think you guys have to do Doppler. But for sound waves, remember we said sound waves are longitudinal waves. So if you have like a speaker, what happens is that the speaker kind of moves the air molecules closer together, so it compresses the air in front of the speaker, and that creates a region of higher pressure. And that's called compression. Then half a cycle later, right, that cone of air will move backwards, and there's pressure decreases. Pressure decreases are called rarefactions. So higher regions of pressure are called compressions. Lower regions of pressure are called rarefactions, right? So right here, this would be a rarefaction because there's not a lot of pressure. Right here would be a compression because there's a lot of pressure right there. There's a lot of particles there, so more pressure here. You really have to know pure tone. Now we're getting to like some plug and chug examples here. I'm not going to go over this whole thing, but they're saying what are the wavelengths of sound waves at the limits of human hearing? 20 hertz and 20 kilohertz, and at the mid-range frequency of 500 hertz. So you know that the speed of sound is 343 meters per second. We know the speed of sound, or at least the equation for it is velocity is equal to the wavelength times the frequency. So now they're just asking for the wavelength. So you have these frequency 20 hertz, 20 kilohertz, and 500 hertz. So we take the speed of sound divided by every single frequency, right? We should be able to get our wavelength. So they did 343 divided by 20, 343 divided by 500, and 343 divided by 20,000 basically. So you get every single wavelength there. But yeah. I doubt you have to like really know all of these different wavelengths, at least for like this exam, so I won't bother with that. But just know that the speed of light is 3 times 10 to the 8 meters per second as well. Also probably don't have to know this. This is just another plug and chug. You guys can probably get this on your own as well. Like this is just an application of this equation once again, so I don't think there's really a point to kind of go over it again. Same thing for this one. It's just they're changing up the units. Now they're doing, instead of hertz, they're doing megahertz and gigahertz. So it doesn't really matter. Going back to the wave stuff again, there is a specific constant here that's called the wave number. This isn't the spring constant. K here is not the spring constant. This is the wave number. The wave number is simply defined as 2 pi divided by your wavelength. That would give you the wave number. 2 pi divided by wavelength is your wave number. K here in the context of sinusoidal waves and sound is your wave number, not your spring constant. Now, There's two equations for sinusoidal waves, whether your wave is moving to the right or moving to the left. These will probably just be found on your equation sheet. If the wave is moving to the right, positive x moving to the right, then your equation is a, your amplitude, times cosine, times, or of your wave number, times your distance that you move to the right, minus your angular frequency times time. So k is your wave number, x is the distance that you move to the right, omega is your angular frequency, and t is the time that you moved, right? If you're moving to the left, amplitude times cosine of your wave number times your displacement to the left, plus your angular frequency times your time, right? So if I wanted to set up an equation for a snapshot graph that looks like this, well, they gave me the amplitude, which is 10 centimeters, which is 0.1 meters, right? They gave me the speed is 6 meters per second, right? Well, I have to figure out wave number, angular frequency, right? Because x and t are just variables. So if I want to figure out wave number, k is equal to 2 pi divided by wavelength. Well, from a snapshot graph, remember, we can figure out the wavelength. So from here to here, what's my wavelength? 2 meters, right? So then 2 pi divided by 2, that gives me my wave number. So my wave number is just simply pi. So I can just plug in pi x. So pi is my wave number. For my angular frequency, I know that's equal to 2 pi over my period, but unfortunately this isn't a history graph, so I can't figure out my period from here. It's also equal to 2 pi times frequency, right? Well, I can get my frequency because they gave me my speed. I know that for speed of a wave, right, that's equal to your your wavelength times your frequency, right? So if my wavelength was 2 and my speed was 6, then my frequency should be 3, right? So my angular frequency is 2 pi times my frequency. Well, if my frequency was 3, then my angular frequency should be 6 pi. And so it should just be minus 6 pi t. The frequency, so I have the velocity of the wave is equal to wavelength times frequency. They gave you the speed is 6 meters per second, and then the wavelength is 2 from here to here. So 6 divided by 2 gives you 3 for your frequency. That's just your regular frequency. And then your angular frequency is equal to 2 pi times that frequency. So 2 pi times 3 would give you 6 pi for your 6 pi radians per second for your angular frequency. So that's pi x minus 6 pi t. Make sense? Oh, okay. And then, yeah, do you have a question? They didn't ask us to plug anything in. They just told us to write the equation. So, yeah, just setting up the equation. But yeah, this would essentially just be equal to your motion of the wave there, your displacement of the particles, right? It would be y is equal to all of that with respect to time, with respect to position. So I think for this problem, I don't know if they, yeah. So that just allows you to figure out the vertical position. So if I were looking at that green bead, that would be the equation I'd use to kind of figure out the position of that green bead, right? Or displacement upwards and downwards. So basically they just use, this is an example where they told you to set up an equation and then they told you to figure out what the displacement is upwards and downwards after a certain amount of time. They already kind of solve it. So just for the sake of time, I don't know if you guys have been here already for a long time, so yeah, I'll just kind of skip this over, but they did the exact same stuff that I did for the previous problem. It's just that now they're also plugging something in like you were talking about earlier. So I'll just skip that over for a second. This problem, so they told you, okay, so suppose a boat is at rest in the open ocean. The wind then creates a steady wave with wavelength 190 meters, so wavelength is 190, traveling at 14 meters per second, right? The top of the crests of the wave is 2 meters above. So the top of the crests is 2 meters above the troughs. So if here are the troughs, here are the crests, right? The crest is right here. Then from here to here is 2 meters. So what is my amplitude? So if they're saying from the top of the crests, those are 2 meters, because this is the trough. If they're saying that the crest is 2 meters above the trough, then what's my amplitude? not 2. 1, right? So it would be 1 because it's from like the 0 point here to the crest, or the distance from the equilibrium to the crest, or from the equilibrium to the trough. So it should be half of that at 1. So that's our amplitude there. And then they're saying what's the maximum vertical speed, right? This you kind of depends on like the information that we had from before. But if they're asking for maximum speed, remember this is from the older chapter, V max would just be equal to your amplitude times your angular frequency, right? And so your angular frequency, you got that from the previous part of the problem. I know we didn't go over it, but you know. So you just take like 1 basically times that angular frequency, and then you just get your V max.
Thank you.
Yep, absolutely. Okay, finally we're getting to like sound intensity levels. So this is from previous chapter once again with energy. Power is just energy transferred per unit time. So power, P of the wave, is the rate at which the entire wave transfers energy, right? And then there's 3 types of waves: circular, spherical, and planar waves. Circular waves, they just look like they sound, just a bunch of circles, right? So that's like if you threw a rock in the water, that'll make that ripple effect right there. Circular wave is 2-dimensional, it spreads across the surface, and then the location of the crests, right? Those would be like your circles here. So at every circle here, that's your crest. So from crest to crest, remember, that gives us our wavelength. So the difference, like the distance between each concentric circle, will give us our wavelength. So from this edge of the circle to this edge of the circle, that's our wavelength. From this edge of the circle to this edge of the circle, that's our wavelength, right? So they're spaced evenly apart, 1 wavelength each. Spherical waves are 3D. Yeah, no worries. All right, I'll see you.
I think you can skip over the low yield stuff.
Yeah, I think like there's.
Just go over the main equations.
Yeah.
Yeah, the intensity equation.
Honestly, after here is just all just
That's
telling the
problems?
equations. Yeah.
Oh, okay.
Yeah. But there's a fair amount, but still, we can get through it here. But yeah, spherical waves would just be in 3D. And that's, I think we use spherical waves for sound, right? Yeah. Plane waves, you don't really have to know. There's not a lot of problems about that. But now we're getting to a concept of intensity, and intensity is just like the strength, quote unquote, the strength of a wave, right? And so you can say like intensity of a sound, we can think about that as like the strength of the sound, essentially. So for intensity, that's defined as the wave's power per unit area. So intensity is just the power divided by area, and those are units of watt per meter squared. But yeah. So if you have a spherical wave source, right? This is usually for sound, I'm pretty sure. So if you have that, and when you figure out the intensity for it, it would be the intensity is equal to the power of the source divided by the surface area for that sphere. And so the surface area of a sphere is 4 pi r squared. You just take the power of the source divided by 4 pi r squared. That gives you the intensity for a spherical wavefront, right? So that's it for spherical waves. For planar waves, where the cross-sectional area basically is just a circle, then it's pi r squared. So your intensity would be equal to the power of the source once again, divided by the area, and that area would just be pi r squared for a planar wave. But yeah, and usually the example is a laser. So yeah, I don't know why, but jeez. No, I'm good. Yeah, a bright, tightly focused laser pointer emits 1 milliwatt of light power into a beam that is 1 millimeters in diameter. So if we have a laser pointer, remember with the laser pointer, that's like our planar waves. So we're going to use this type of equation here, which is the power divided by pi r squared and not by 4 pi r squared. So if we want to figure out the intensity and we have the power here as 1 milliwatt, then we just plug in for our area here. We just take the diameter, convert it to the radius. So that's 0.5 millimeters for our radius. And we just take that pi times that radius squared, and then we have the power, and we can just divide that. So your power there, that milliwatts, that 1 milliwatt would be 0.0010 watts. And then your radius, the 0.5 millimeters, that would be 0.00050 meters. And then you just take pi r squared, take the power divided by that. That should give you your intensity there in units of watt per meter squared. This is a very niche kind of specific example here. So they said, suppose you're powering a spacecraft with a 2 meter squared area of solar cells with an efficiency of 12%. So by efficiency of 12%, they mean that it's only using 12% of the incoming energy, right? So area is 2 meters squared. They gave us the intensity is 1300 watts per meter squared. So now they're asking for the maximum power, right? Well, for the maximum power, we know that intensity is equal to the power of the source divided by the area. Well, the area is 2 meters squared, right? Now, intensity is 1300 watts per meter squared like they gave us. So if you take 1300 times 2, that's 2600 watts for our power, right? Do we end there? No, because remember they said you can only use 12% of that energy. Power is energy per unit time. Well, we're assuming the time's constant, so the only thing that would change then is the energy. If we're using 12% of that energy, we're using 12% of that power. So 12% of that power would just be 0.12 times that power that we figured out, the 2600. So this would be optimal, but in reality we only get 312 because it's only at 12% efficiency. If we then wanted to figure out what is the total power output of the sun, then we just take that, what did I want to say? Yeah, so we take that intensity is equal to power divided by the area once again, and the intensity is 1300 watts like they gave us, and then if we want to figure out the power, then we can just multiply that by the area, right? And so the area here for the sun, obviously the sun is a sphere, so it would be 4 pi r squared, and then the r that they gave us was, here's the radius for, or the distance away, which is 1.52 times 10 to the 11 meters away, right? So this would be like our radius. You just take that, square it, times 4 pi, and then times your intensity gets your power. Makes sense? It's just a rearrangement of variables to figure out your power of the source. A solar panel in orbit around the Earth absorbs 1 watt of solar energy from the sun. How much energy would this panel absorb at Jupiter? So if we're absorbing 1 watt of solar energy, right, then our power is just 1 watt. Now we want to figure out what the energy is at Jupiter. Well, if we're assuming the same time, whatever change you see in power, you should see the same change in energy, right? So if it's 5 times further away, what does that mean? Like if you're at a different distance, what does that mean in terms of our intensity, our power, and all of that? What does that indicate? If we have, remember we have intensity is equal to the power times or divided by your area, right? Well, we want to figure out what the new power is because they're asking us about the energy. And power obviously factors energy per unit time. Obviously the time is going to stay the same because there's no indication that the time changed. So we're looking at intensity is equal to power over area. If we want to figure out the new power, right, given that it's 5 times further away, what has to change? The area, right? Because if you went 5 times further away, well, then that would mean 5 times your radius, right? So 5 times your radius would give you your new distance away. So if this is a sphere once again, 4 pi times 5 times the radius squared, right? That would give us 25 times basically your what's it called? 25 times the area, right? So if it's 25 times the area, what do I want to say? Shoot. I'm so tired. I'm sorry. Give me a sec. So if our power is one, okay, so our intensity is power over area. Our power is 1 watt. Our area now is 25 times that. Okay. Well, that's kind of weird because in that case, they would just be asking about the intensity. Yeah, I'm not quite sure why this isn't working out.
That's what I was thinking. I managed to get it, but I was like,
Yeah, I don't remember how exactly I got it, but
how would you take out the pi?
well, the pi's would cancel out because, like, I mean, just your everything cancels out. But I'm like the way it's looking like, so I is equal to power over area, right? If I change the area, then I should be changing the intensity. But they're asking about the energy, so like if I can't necessarily just multiply it over I times A, and that's equal to power, because the proportions aren't. Well, I wouldn't say the proportions are the same, but like you don't have the same relationship. So you can't just say like, okay, well, it's 5 times the distance away, so it's 25 times the area, so 25 times the intensity, right? Then it's just 25 times the power, right? You can't just say that it's 25 watts, right? You can't do that. But let's say like, okay, what if we did that? So if I did I is equal to P over A, where this is just 1 watt, and 4 pi r squared, let's say this is 1 squared, right? So 1 over 4 pi is my intensity. Well then, 4 pi times my intensity would equal 1 watt. Well, okay, hold up. Okay, let me just skip this for now, and then I'll try and come back later to it if I can. Otherwise, I'll just like send an explanation for this stupid problem because I just can't think anymore. That just brings us to sound and decibels. I think this is the last topic. There's only like 9 slides left, so we're good. All of this right here just tells you that sound intensity level is on a logarithmic scale. And so on the next slide here, this is the equation for sound intensity level. That's your beta here, right? So for this equation, it integrates a couple of different like variables and features. So it's 10 decibels times log base 10 of your intensity divided by intensity sub 0, which is just the threshold of hearing. So threshold of hearing is the lowest intensity of sound that can be heard, and based on that like threshold of hearing, that's where we place the 0 for our loudness scale. So if we were to hear something at an intensity of 1.0 times 10 to the negative 12 watts per meter squared, if we plugged this into the equation, 1.0 times 10 to the negative 12 divided by 1.0 times 10 to the negative 12, what does the inside of the parentheses look like? What's the value? We're taking the same value divided by the same value, just 1, right? So log base 10 of 1 would be what? Not quite. 0, right? Because this log base 10 of this just tells you like 10 to the x is equal to 1, and x would have to be 0. So if this whole section here is 0, then 0 times 10 decibels would just give you 0 for your sound intensity level. So that's why at the threshold of hearing, it's 0 decibels, right? And then what they do here is just kind of do exactly what I did, which is just plug it in and see 10 to the 0, all that. These are different values for different intensities and sound intensity levels for different sounds. Yeah, I know. But then we have, if we were to rearrange the equation in a way, we could have our intensity that we can get as well. So our intensity would be the threshold of hearing times 10 to the power of your sound intensity level divided by 10 decibels. So this is just kind of a rearrangement of the original equation. Basically, we can kind of use these two equations, plug in different intensity values, different sound intensity values to get one or the other. And so all of the examples for basically the rest of this like slide would just be like rearrangements of these equations to figure things out. So if they told you your eardrum has a diameter of approximately 8.4 millimeters, how much power is being received by one of your eardrums? So our diameter is 8.4 millimeters, right? They gave us the noise level of 90 decibels. So 90 decibels is our sound intensity level there at that point. And our diameter is 8.4 millimeters. So you might be thinking like, well, what does the diameter have to do with anything? Well, remember, intensity is equal to power divided by your area, right? So the idea here is that like if they want you to, never mind. They're asking you about power. So if you know that intensity is equal to power over area and they're giving you diameter, well, you can adjust and figure out your area value, multiply it by your intensity, and then you can get your power. Well, how do we figure out the intensity at a value of 90 decibels, at a sound intensity level of 90 decibels? Well, we can use that intensity equation, right? We have the threshold of hearing times 10 raised to the sound intensity level divided by 10 decibels. So if we're at 90 decibels, 90 divided by 10, that's 9, right? So 10 to the 9th times 1 times 10 to the negative 12, right? And that would give you your intensity level, or your sound intensity, right? So once you have your intensity, right, they did 10 to the negative 12 times 10 raised to the power of 90 divided by 10. So 10 to the 9th times 10 to the negative 12, that gives us 10 to the negative 3 for our intensity. Then all they did was intensity is equal to power over area. So they just multiplied intensity times pi r squared, right? Where the r was 8.4 millimeters, right? So radius here, 4.2 millimeters, and they just calculated things out. They ended up with value of nanowatts, which I don't know why, but generally everything is going to be in watts, unless otherwise stated. So they just did some weird conversions, but yeah, it would be equivalent of 55 nanowatts. And then for part B, they're saying the level of noise is damaging over a long time, so you use earplugs that are rated to reduce the sound intensity level by 26 decibels. And then what is the power received by one eardrum now, right? So we want to figure out the power again. So remember, the power then was determinant on the intensity is equal to power over area. Well, if we're keeping the same area, but now we're changing the intensity level, or at least the intensity, the intensity is dependent on the sound intensity level, the decibels, right? So if we dropped it 26 decibels, we can plug in 26 here, right? And so then we see that it's 10 to the 2.6, right? This part right here, 26 divided by 10 is 2.6. So 10 to the 2.6 times your threshold of hearing, right? So essentially what we see here is a decrease. This would be like the decrease of your sound intensity by a factor of 10 to the 2.6. Because remember, we did 10 to the negative 12 times this stuff right here, and that was 10 to the negative 3. What we did is basically the same thing. We did 10 to the negative 12, but now we're multiplying by a factor of 10 to the 2.6. So 10 to the 2.6 is what we decrease it by. We decrease it by a factor of 10 to the 2.6. So in order to figure out the new power, well, we have this power of 55 nanowatts here. If we divide 55 by a factor of 10 to the 2.6, we should get 0.14 nanowatts. So we decreased it by a factor of 10 to the 2.6, which is the same factor that the sound intensity decreased by. So we just divide 55 divided by 10 to the 2.6 to get our new power of 0.14 nanowatts. I think you can also do it the longer way, which is if they're just asking what the power is, you can find the new intensity again. So if you just take the intensity, right, from before here, this equation, if it dropped 26 decibels, you went from 90 minus 26, right? So that gives you 64 decibels as your new sound intensity level. So if you plugged in the 64 here, divided by 10, did all of this, got your new intensity, right? Once you have your new intensity, then you can multiply it by the area again and then get your new power, right? So you could do it that way as well, I think.
So it's sweet.
Yeah. But that's that example problem there. I think this is the final example. Yeah, this is the final example problem. They're saying at a distance of 10 meters from a small loudspeaker, you measure the sound intensity level to be 80 decibels. So sound intensity level, that's your beta. Sound intensity level is measured in decibels. Sound intensity is watts per meter squared. That's different. That's I. That's sound intensity. So sound intensity level is your beta. And then sound intensity is your I. Right? Now they're asking what will the sound intensity level be at a distance of 20 meters from that speaker. Once again, if we change the distance, right, if we're looking at intensity versus sound intensity level is dependent on intensity, but at the same time, what is intensity dependent on? It's power divided by area, right? If we're changing the distance, we're changing the area. If we're changing the area, we change the intensity. If we change the intensity, we change the sound level. And so that's what we're trying to do here. We're trying to figure out how does this change in the distance changing our intensity, and how does that change in intensity change the sound level, right? So first of all, we want to figure out what the new intensity is at that new distance, right? Then, or at least my bad, we're trying to figure out what the intensity is at this 10 meter distance first. Then we figure out the new intensity at 20 meters, and then the sound intensity level at a distance of 20 meters. Because remember, the sound intensity level factors in this intensity at that specific distance divided by your threshold of hearing. So for the intensity at the 10 meter distance, right, you take the intensity equals the threshold of hearing times 10 raised to the sound intensity level divided by 10 decibels, right? So our intensity level initially was 80 decibels. So we take that 80 divided by 10, that gives us 10 to the 8th, and then multiply by a threshold of hearing, that gives us our intensity at 10 meters, right? Then they're saying, okay, well, if you increase the distance to 20 meters, you double the distance. Think about the distance as your radius in this case for your area. So if I doubled the area, if this is pi r squared, right, or if, if it's like pi r squared, right, then if you doubled the radius, what does that happen? What does that cause a change in your area of? So if it's pi r squared, and now it's pi 2r squared, 4, right? So you multiplied your area by 4, and in a case like intensity is equal to power over area. So if I multiplied the area by 4, what happened to my intensity? It's 1/4, right? So instead of like going through and doing all of this step again, right, then I can just take my intensity divided by 4. So this intensity right here divided by 4, and that gives me 0.25 times 10 to the negative 5 watts per meter squared for my new intensity. Then finally, when I'm trying to figure out the sound intensity level at that 20 meter distance, all I would do is take the sound intensity level equation, right? Plug in that new intensity level at 20 meters, which is that 0.25 times 10 to the negative 5, divided by threshold of hearing, take the log base 10 of that, multiply by 10 decibels, and that gives you your new sound intensity level. I think that's it for this chapter. So thank you for those who are watching online. Thank you for everyone who came today. Good luck with the exam next week. I will most likely come Wednesday. I don't know. I'm still kind of figuring things out, but will definitely be here. I just have to figure some things out, so we'll see. But this stuff, all of these sessions have been recorded and uploaded on YouTube. The only exception is weeks 10, I believe, was not recorded. We just recorded week 11 because I already had a quiz review for week 10. So with that being said, I think that should be it. That wraps everything up. So thank you everyone again.